Hello there, Mr. Sutton here, bringing you this lesson on improper integrals. In this one, we're going to be evaluating definite integrals that are either unbounded or undefined in certain places. For your warm-up on this one, see if you can fill in the blanks. All right, let's see if you found out what we need for the FTC. So if a function is continuous on the closed interval from a to b, then integral from a to b of f of x dx equals big F of b minus big F of a. Essentially, if we have these conditions, we're guaranteed that we can evaluate an integral like we're doing over here. But what if we don't have one or both of these conditions? What if we have something like example 1 down here with an integral from, say, negative infinity to negative 1 over x squared? Well, in that case, we don't have that closed interval anymore. What we have is something called an improper integral. So this is an integral that has either infinite limits or discontinuities between the limits or both. So how do we deal with a situation like this? Well, there's a reason I started with an example that had an infinity in it. In general, when we're dealing with things with infinity, we usually have to use limits because you can't plug in infinity. You can only approach it. So our strategy on this is going to be to rewrite our improper integral with a limit as we approach the trouble spot. So I'm going to rewrite this as the limit and I'm going to substitute a letter for this. I'm going to call this lower limit a. So I'm going to say limit as a approaches negative infinity of, and now we have the integral from a to negative 1 of 1 over x squared dx. So you might be wondering, well, how is this really any different than what I have over here? The way it's different is I've incorporated a limit now, and it's legal to approach negative infinity. It's not legal to plug it in like our integral implies over here. Okay, so we've rewritten this a little bit. What do we do from there? At this point, we are going to integrate as normal, and then we're going to keep our limit notation until we actually plug in our limits of integration. So we'll do this one together so you can see how things play out in a situation like this. Now, before we go any further, would you like to speculate on what we're going to get for the area under this curve? It's kind of interesting because we're going forever in one direction. So does that mean we end up with infinite area? Let's find out. So the antiderivative of x to the negative 2, which I rewrote it like that to make it easier, that's going to be negative 1 times x to the negative 1. So negative 1 over x, then I'll rewrite that as from a to negative 1. And again, I'm keeping my limit notation until I actually plug something in here. And even after that, actually, until I actually take the limit and plug something in for a, I'm going to keep this limit notation around. So expanding this now, I've got negative 1 over negative 1 minus, or actually it's going to be plus because we're subtracting this negative thing here, so plus 1 over a. Again, limit is still sticking around. At this point, though, I'm actually going to have to plug in negative infinity, if that's such a thing, and see what this comes out to. So negative 1 over negative 1, that's just going to be positive 1. How about 1 over essentially negative infinity? Well, that's going to be 0. So then that adds up to 1, which is kind of interesting because you have an infinite distance that you're going to calculate this area, but you get a finite number. So let's talk about what this result means. If you get a finite limit, because all we actually did here was take a limit, that means that your integral converges to the value of that limit that you just got. This number here is the value of this integral here. But let's say you get either an infinite limit or a limit that does not exist for some other reason. Well, in that case, we would say your integral diverges, which is to say your integral has no value. So here's another example for you to try. Pause the video and get as far as you can on this one. All right, so we definitely need to use a limit on this one. We have a limit of integration that's infinity, so this is an improper integral. I'm going to rewrite this as the limit as b approaches infinity, and I use b for the upper limit every time, but you can use whatever letter you want. And I've got the integral from 2 to b of all this stuff. And so now we have to actually integrate this. Well, we see here that this is going to be kind of a pain to integrate. We have an inner function, though, whose derivative is somewhere else in the problem. So this is actually going to involve some substitution. And I'll just throw it out there, about half of the questions on the AP exam that have improper integrals require u substitution for whatever reason. So let's go ahead and go through that process. Feel free to pause the video if you didn't see that initially and try it yourself. All right, so I'm going to let my u value here be e to the 2x, actually just 2x to the 5th. I just want that piece to be u. And then du, that's going to be 10x to the 4th dx. And then isolating dx, I've got du over 10x to the 4th. I'm also going to have to do limits of integration now, because right now this 2 and this b are x values. I need them to be u values. So if x equals 2, then u is going to be 2 times 2 to the 5th. That's essentially 2 to the 6th, or 64. And if x equals b, then this is a little bit easier. U is just going to be 2b to the 5th. All right, plugging everything back in. We're going to have the limit as b approaches infinity. That's not going away. Of now I have my limits as 64 to 2b to the 5th. And in here, I've replaced this 2x to the 5th with u, so I have 30x to the 4th, e to the u, and then dx I'm swapping out for du over 10x to the 4th. Simplifying this a little bit here, the 10x to the 4th and the 30x to the 4th reduce nicely to just 3, so I've got all of this stuff times 3 e to the u du. Now for the antiderivative, well, that's actually pretty convenient on this. It's just 3e to the u. I still have my limit in there, though, so limit as b approaches infinity of 3e to the u, evaluated from 64 to 2b to the 5th. Let me go ahead now and plug both of these things in, and I'm going to yank a 3 outside as well. So I've got the limit as b approaches infinity of 3 times, and now inside I have 3e to the 2b to the 5th minus 3e to the 64th. Now, these are both pretty big numbers, but I think you can agree that as b approaches infinity, this term right here with the variable in the exponent is going to dominate this expression. So this just ends up being like the limit as b approaches infinity of e to the 2b to the 5th, and we can see this term here is approaching infinity. This whole limit is approaching infinity. Well, what does that mean? If we end up with an infinite limit or a limit that just flat out does not exist, our integral diverges. So we actually get no value out of this one. We'll do one more example just to give you the full variety of these. Now, on this example, if you just kind of blindly integrate this without thinking about it, you're like, okay, antiderivative of 1 over x is ln of absolute value of x. ln of 1 minus essentially ln of 1 is 0. Hey, I'm done. There's a problem, though. 1 over 0 would be undefined, and we have 0 between these limits of integration. So because of this discontinuity at x equals 0, we have an improper integral on our hands here. So how do we handle it if we have some kind of discontinuity? Well, what we're going to do is essentially split this up into two different integrals. So for discontinuities, you always have to split up the integral and have one integral where you're approaching from the left side and another where you're approaching from the right side. So let me show you what this looks like in practice. We're going to have to use limits. I'm going to need a limit as b approaches 0 from the left side of negative 1 to b 1 over x dx. So this is essentially taking the piece of this function that's to the left of 0. And I'm getting as close as I can to 0 without actually plugging it in. But I'm not done. I have the other half now. I have to add the limit as a approaches 0 from the right side of a to 1, 1 over x dx. So this is everything on the right side. And since this is my lower limit here, this is my leftmost value, I have to approach that from the right. And since this is my rightmost value, this b value, I have to approach this from the left. So just be careful writing which direction you're approaching from on these limits. But now that we've done that, pause the video and see if you can take it from here. All right, so antiderivatives, we already said that was ln of absolute value of x. My limit is still hanging around, so I'm just basically copying the limit down here, and now I've got evaluating from negative 1 to b, ln of absolute value of x. Pretty much the same deal on this other one, except with a different limit. Same antiderivative, though, just different limits of evaluation here. And we could actually go the whole distance and plug all this stuff in, but if you're looking ahead here, you'll notice that we're going to have to plug b in here, and the limit as b approaches 0 from the left side of ln of absolute value of b, essentially, as you plug in 0 to the ln function, you're riding an asymptote down to infinity, or you just don't have anything on the left side there. Either way, this is going to be undefined if you're plugging in 0 from one direction or another to the ln function. So because that limit does not exist, what does that mean for the whole integral? Do we have to go over here and check this out? You could if you wanted to, but as it happens, if either of these limits diverges, then the whole integral diverges. If you have some kind of infinity or undefined somewhere, that just messes everything up. So we're going to say that this whole integral then diverges. So that's it for this one. I mean, I could just keep doing these forever, but that would be improper. Until next time, Mr. Sutton signing off.